Okay, so let's finish this Laplace, the transfer function, okay, and then we'll look at the relationship between transfer function and the impulse response. Okay. Then we even got time, we'll go on to a new topic called Fourier series. Okay. Yeah. Okay, so here's a quick review as to the definition of transfer function. Okay, so transfer function of an LTI system, okay, is given by the ratio of the Laplace transform of the output over to the Laplace transform of the input. So basically we use h of s to represent this transfer function of the system. And it's the ratio between the Laplace transform of the output over the input. And don't forget this important assumption, assuming all initial conditions are 0. Okay, because you need this assumption to derive the transfer function. So let's say I'll give you a quick some examples here. Okay, 3y prime plus 4y plus 4y prime plus 2y equal u of t. The other one, let's say y prime plus 3y equal to sine omega t, which is sine t. And yeah, let's just maybe just these two should be okay. Okay, what will be the Laplace transform of these two systems in here? Okay. So what do? We take Laplace transform. What is the transfer function? We take a Laplace transform of both sides of the equation. Okay. So when you take Laplace transform both sides of the equation, particularly for those second order and the first order derivative, according to the table, you do have the initial condition got involved, right? But however, because we're looking for the transfer function, so we put all of the initial conditions 0. So all you need to do is just change this one to 3s squared capital Y squared 4s capital Y of s plus 2 Y of s equal to u of t's Laplace transform is 1 over s. Okay. So, but in this particular case here, okay, this is what you do when you take a Laplace transform in here, right? Okay. But however, you see, when I'm looking for transfer function does not depends on this x of s. Okay. Look at this transfer function. It's just the ratio between the y of s and x of s. So where's x of s come from? X of s come from here, right? From x of t. So in this particular case, which is my x of t? So let's say this is my x of t here, right? This is my x of t. So it's just that in this particular case, you know what x of t already, right? But the transfer function does not depend on the input. It's a characteristic. It's basically a property of the system. So it doesn't change even if you change the input. You see what I'm saying? Okay. So the input is here is x of t. So really, you don't really need to care about this 1 over s here. So if you know this is x of t over here, and then all you need to do is, okay, just represent this side as x of s at here. Okay, yeah. Because you're not looking for ratio between y of s and 1 over of s. You're looking for ratio between y of s and the general input x of s, right? So you're not looking for a general input here. So the question probably should tell you exactly, maybe the question is, here's my system, and x of t equal to u of t, such like that, right? And here's a system, and the x of t equal to sine 2t. Okay. And what will be the Laplace transform, right? Yeah. So then when you take Laplace transform both sides of this equation, if you are required to look for the transfer function, you don't have to plug this u of t into this one here, right? Yeah. But then you probably would need that in the next step, okay? But for the time being, if I'm looking for the transfer function, and all I need to do is just change that x, small x to capital X, okay, and the corresponding t to s, that's the Laplace transform, right? And then look for the ratio now, looking for the ratio between the input, the outputs over the input. Okay. So what's my Laplace, what's my transfer function? It's y of s, yeah, over x of s, in this case, which is 1 over this, right? It's this, okay? So you see that I really don't need to put this u of t over here. So if you're looking for transfer function, that's what you do. But however, of course, the next step is then where we're going to talk about impulse response. Basically, we say what's the impulse response. Then I'm going to have to actually not. If we're talking about what's the impulse response, or if we're talking about what's the system output, okay, for this one here, then you need to put the u of t into this differential equation right here. Okay, but for transfer function, this is what you do. Okay. Yeah. Any questions? All good? Yeah. Second one here, okay, transfer. Let's say the transfer function for this system here. Maybe I'll change the system just slightly, just a little bit different. Okay, here's my system here. Okay, here's my system, and this is the input. Okay, input it here. Okay, yeah. So what's the transfer function? So what do? You take Laplace transform both sides. So this is s, y of s, plus 3 y of s. Okay, yeah. And this side here is dx of t over dt, and the Laplace transform that is s x of s, right? Okay. So overall, your transfer function, which is s over s plus 3. Okay. Yeah. Is that clear? Okay. So, giving a differential equation, okay, representing a certain system. Okay, know what's the input, know what's the output. And then if the question is simply to ask the transfer function, you take Laplace transform both sides, okay, without a concern of what exactly is the current input, okay, just take it a general input x of s, x of t, okay, and then find the ratio between y of s and x of s. That's the Laplace, that's the transfer function. Okay. Okay. So now the next question is, what's the connection between the impulse response, transfer function and impulse response? Maybe I need to point out one more thing here before we move on here. Okay, so based on the transfer function, okay, h of s. Okay, so let's say my h of s is an expression between the numerator and denominator, right? Yeah. So let's observe a few things right here, right? Yeah. Number one, okay, if I set this d of s equal to 0, so let's see, based on the examples I just showed you right here, okay, let's take a look at this d of s. What exactly d of s here? So you can see this one here. Where's d of s? It's this term here, right? It's this. So 3s squared plus 4s plus 2. So for this guy right here, okay, if you go back to the second order one here, if you remember when we were talking about solving this differential equation in time domain, and what's the first step that we do? We find the so-called characteristic equation, right? Yeah. The characteristic equation in this particular case, which is what? 3 lambda squared plus 4 lambda plus 2 equal to 0. That makes sense, right? Yeah. So if you look at this characteristic equation here, what's the difference between this one and the denominator equal to 0? The only difference is what? That's this is s, that's lambda there, right? Yeah. So this is actually why you say this d of s equal to 0. basically is the characteristic equation that we have been talking about. Okay, so this is the characteristic equation. Okay. Of course, when you're solving the characteristic equation, you got a solution for those lambda. So we just call lambda the roots of the characteristic equation there, right? Yeah. But in this particular case, we can give it a different name now. This d of s equals 0. So the solution for this one here, we can call this, those are poles of the system. Okay, so solution at here, okay, are called poles. Yeah, I think I mentioned about this concept in some previous lectures. Okay, so the solution of this are called poles here. Okay. Now, yeah, maybe let's just finish the next one, then we'll see this thing here. Okay. So then, if I set the numerator to 0, yeah, this one never seen it before. We set the numerator to 0, and the solution, I think I mentioned this one, solutions are called zeros. Okay, they're called zeros. Okay. Okay. And the other thing is, we often talk about the order of the system. You know, when you have a differential equation, okay, when you have a differential equation, how do we identify the order of the system? The what? That's right. The highest order of the derivative, right? The midterm questions there. So in this particular case, if I have a transfer function, then how do I determine the order of the system? What do? I basically look at the order of this denominator at here. Okay, so this order of this d of s is the order of the system. Okay, so you look at the previous one, s squared plus something, so the order of the system, second order, right? Yeah, so that's the idea here. Okay, yeah. Okay. Now, the poles and the zeros are very important concept in terms of this control system and also in terms of linear system response. All right, and if you remember, when we're having a characteristic equation, let's say y double prime ay prime plus by, okay, equal to f of t, right? Okay. So the first step is n lambda squared a lambda plus b equals to 0. That's what we generally do, and we find there's 3 cases. Remember that? There's 3 cases. If when I was talking about this concept called forced vibration, I used a mass spring damper system. So m, okay, basically m lambda squared plus b lambda plus k and equal to 0. That's the characteristic for a mass spring damper system, right? Yeah. And we were talking about, okay, what are the 3 different cases, or what are 3 different names for a mass spring damper system? So one is underdamped, overdamped, and critical damped, right? But however, you know, whatever the name's called, that all depends on the solution of this characteristic equation. And for this particular case here, if you remember, there's 3 cases too, and one was different name. We just call it two distinct real roots. 2 complex conjugate roots, and 1 case is the double roots, right? Yeah. But no matter what, we notice basically the solution y of t. Okay, so whether this y of t is so-called stable or not really depends. It really are determined by the lambda solution of the lambda here, right? So this guy stable or not, okay, is determined by this, okay, lambda value, okay, lambda values. So for example, right, if lambda value or the s value, in my case is a characteristic equation or the poles that are here, so lambda s is the same thing now. So for example, if okay, s, okay, 1, let's say I have two distinct real roots, okay, s1 and 2, but in both of them are less than 0. Okay, both of them less than 0. So technically, the solution will be what? The homogeneous solution will be C1e, right, lambda 1t plus C2e lambda 2t, right? Yeah. So if lambda 1, lambda 2, or S1, S2 here, both are less than 0, so those two exponential terms, as t goes to infinite, those two exponential terms will decay to 0, right? So that's basically what we call a stable situation, right? Stable. However, so this is stable here, right? However, if these two are greater than 0, then you're going to have unstable situation, right? So basically what this tells us is those S1, S2, which is called the poles of the system, the location of the poles of the system determines the stability of the system. Okay, that's basically the idea here. Okay, now S here is the location of the poles. So S could be two real poles, could be two different real poles, could be two conjugate complex poles, or could be one double roots, right? Double poles. Okay, so basically repeated poles at one location. If it's high order, third order, fourth order, so you can have many poles as possible, right? Yeah. But no matter what, if I look at the location of the poles in the S plane, basically in the complex plane, because you know S is what? S is a complex number. Okay, S is a complex number. Okay, so the S here, if I look at it in the real and imaginary, the complex plane, so the S could be here, 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 or here, right? Yeah. Now, if I see it, let's see if S is the real numbers, then where is S? It's everywhere here, right? If S is a complex conjugate numbers, then it's going to be either here, here, here. So when you talk about complex conjugate, it's always a pair, right? So for example, S could be here, here. That's a pair complex conjugate roots. Okay? Yeah. And it could be a real. It could be here. Okay? Yeah. So what we generally do is we use a cross. Okay, this is not a cross. We generally use a cross to represent the poles. We can use a circle to represent, okay, a 0. Okay. So for example, if I have a h of s, okay, which is 2s plus 3, okay, 9s squared plus 12s plus 13. Okay, so here is a transfer function. Okay, so if I take set a denominator to 0, and I can find that this S12 equal to negative 2 plus minus G3 over 3. Okay, so here's a solution for this one here. So if you look at this one here, this is basically a pair of complex conjugate roots, right? Yeah, and the location where it is the real part is less than 0. So the real part is less than 0, and it's going to be somewhere here. And the imaginary part is 3 over 3 is positive, it's 1, okay, and positive and negative 1 here. So basically, if this is 1, and this is negative 1, and this is negative 2 over 3, so that's S1 and S2, right? That's S1, S2, okay? And the 0 right here is, when you set 2s plus 3 equal to 0, you got s equal to negative 2 over 3. So the 0 over here, so 0 is actually coincided here. That's the 0 for this system here. Okay? Yeah. Now, if I ask you, what is the stability of the system? Do you think the system will be stable or unstable? Exactly. It's going to be stable because the real part of this poles here is it's a negative number. Or in other words, the location of the two poles are where? Are on the left side of the S plane. So that's actually an important conclusion I'll tell you here. So to have a stable system, okay, the poles, okay, of the system, okay, have to be on the left side of the S plane. Okay, S side S plane. Now, a natural question is, what happens when the pose is on the imaginary axis? So right at the boundary, right? For example, let's say my h of s is 2 over s squared plus omega squared. Okay, let's say maybe plus 2 squared. Okay, plus 2 squared. This is my transfer function. Okay, yeah. So in this particular case, okay, and this is basically more of like a system y double prime plus 4y equal to 2 equal to this is let's say 2, right? Yeah, equal to a 2 delta t. Okay, like impulse response like this, right? Yeah. So we'll talk about next time. So the transfer function of this one will be this. Okay. Yeah. So as you can see now, what's the pose of here? The pose is s squared plus 2 squared. So you set this denominator equal to 0. You got s1 and 2 equal to positive negative j2, right? So your location is here and here. Okay. And if you try to solve, let's say if you're going to solve the homogeneous one set equal to 0, so the YH would be, what's YH for this system? No, YH homogeneous one, homogeneous solution. You remember that? Cos 2 theta C1 plus, that's right, YH. So the YH is this, YP depends on the input here, but just looking at the YH here, you know, if you plug in initial condition, you get some C1, C2. But however, this YH basically is a constant oscillation in here, right? Yeah, it's not going crazy, but it's constant oscillations.
Is that considered a stable system?
That's right. It's called a marginally stable system. Yeah. So when it's sitting on the edge, it's marginally stable. Yeah.
You did not make a details of that last number, chapter 13.
Oh, 13, yeah. Well, oh, I need to S here. Yeah. Okay. So when pose on imaginary axis, okay, then you probably will have so-called marginally stable system. Okay, marginally stable system. Now, however, there's one special case, okay, and that's when you have 2 repeated poles at the origin, or even higher when you have 3 repeated poles on the origin there. So then what happened? So let's see. Yes, very good. Yeah. So let's say give you an example here, right? Let's say I have a system. Let's say the system is basically just m x double dot equal to equal to f of t. Okay? Yeah. So this what kind of system is this? This is basically mass multiplied by the acceleration equal to the force, right? Yeah. And then let's say if I have a constant force at here, okay, maybe constant force all the way through, right? Yeah. And then what's the Laplace transform of the system? It's going to be m s squared x of s, okay, equal 3 over s, right? 3 over s. Okay. Yeah. So basically, then my x of s, okay. Let's consider initial condition of 0. Okay. So the x of s will just simply equal to 3 over s divided by 1 over s squared and divided by 1 over m, right? Let's say m is 1, so that term is gone. Okay. So basically, now you can see now what's the solution at here. You see this one here. If I only look at this 1 over s here, which is basically a transfer function here, okay? Then how many poles do I have? I have these 2 repeated poles at here. That makes sense, right? Yeah. Now, before talking about the pose here, if I just look at this one here, what do you think the system will behave? Because you apply a constant force to the mass. Exactly, it's going to keep going, right? Yeah. So the acceleration is going to basically keep accelerating, and you have a position keeps going up, right, to infinite, right? That's basically what we call an unstable system. Okay, so the response goes to infinite, right? So then you can see apparently this system has repeated poles at the origin. Okay, so that's another point here. When you have a repeated poles at origin, okay, then you have an unstable system. Okay. So the control system, basically, when you design a control system, okay, many times the whole purpose of designing a control system is essentially boils down to where do you place the poles of the system. So here is the system, right? I can't change it anymore. I'm controlling the system, or I'm controlling dynamics of the response of the system. So then you're going to have to manually plug in another module before the system. That's what we call the control system. Okay? So then what the control system does is essentially you're going to try to change the response of the system, right? Yeah. And of course you want to change that according to the way that you want it to. Right? So the design of that is purely based on your specification. And of course, number one rule that when you design this control system is you need to make sure the poles of the whole system to be on the left side of this S-plane, right? And where exactly going to be? That's a different issue, right? That depends on other customer requirements. Okay. Okay. So any questions on that particular issue there? Okay. Good. Yeah. So now let's talk about the connection between h of s and impulse response. So here we're kind of connecting the dots here, okay? Yeah, impulse response. Now if you remember, when we're talking about the impulse response, the definition of that is very simple. So impulse response is called, okay, so h of t, okay, that's the impulse response, okay? Yeah. And this is when input is delta t, right? It's just as simple as that. Yeah. So when input is delta t, then the output is called impulse response. Okay. Now, let's say I'm gonna go back to use a specific example here to illustrate my idea here. Let's say this is my system here. Okay, this is my system. So I'm gonna rewrite it 3y here. So let's say this is my system. Okay. Here's my system. Okay. And we know that when we're talking about this system, and we can derive our transfer function. Okay. So in this particular case, my transfer function is 1 over 3s squared plus 4s plus 2. Okay, so this is a transfer function, right? Yeah. Okay. So this is nothing new in here. This is what we just learned. This is transfer function. Now let's relate to the definition of impulse response. Here's the system. When you put in x of t, the corresponding output is y of t. And now if I say, how do you obtain the h of t, impulse response? What do? You change this x of t to delta t, right? Yeah. So you set x of t to delta t, okay? Then this y of t becomes this h of t, okay? Or the solution, right, will become this h of t. That's the idea here, right? Yeah, that's the idea. Now, let's relate what the idea here to this to the specific of this transfer function that we just derived here, right? Yeah. Okay. So when you set this x of t to delta t, then what is the transfer function for what is the Laplace transform for x of t, which is when you set this one here, the x of s, which is what? 1. Right? If you look at the table, that's 1. Okay? Yeah. So now I'm gonna move back over here. Okay, move back here. Yeah. So see, this is a y over s over x of s equal to this, right? Equal to this. and which means y of s equal to x of s multiplied by this guy. Okay, does that make sense? Yeah. And now, what I just did is, I'm changing my input to impulse signal. Or in other words, my x of s, capital X of s is 1, right? Is 1. So when x of t equal to delta t, this capital Y of s, which is the output of the system, becomes this, right? Becomes this. And what's this guy here? What's this? That's basically h of s, the transfer function, right? That's basically the transfer function. Okay, that's basically transfer function. So when you set your x of t to delta t at here, the corresponding, the Laplace transform of the output basically is the transfer function. So what are we looking for? We're looking for y of t, right? We are looking for this output in the time domain. And the y of t is the inverse Laplace of this y of s. Okay? Now in this particular case, when your input is delta t, instead of just writing as the inverse Laplace y of s, it's the same thing as h of s. Okay, h of s. So your y of t at this stage is called impulse response, which is represented by h of t. So your h of t, or the impulse response, is basically the inverse Laplace transform of the transfer function. You see the connection now? So let me write down here. So impulse response, okay, is basically the inverse Laplace of transfer function. Okay. So now, there's comes a very simple question. The first part of the question, okay, you have a system now. The first part of the question is, what's the transfer function? Right? You derive it as it is. The second part of the question will be, what's the impulse response of the system? So what do? You take inverse Laplace of what you just find for the system, right? Can you calculate the inverse Laplace of this guy here? I think we can, because we have 3 different cases, right? We can decompose this one into the simplest form, okay? And then looking for the table from the Laplace transform to find the inverse Laplace, and that'll be the impulse response. Okay? Yeah. Is that clear? Yeah. Okay. So let's see, for example, right? What is the, if I see, okay, for this guy here, what is the impulse response of this system in here? So what do? This is what you do first, right? First step, here is the transfer function. So what's the impulse response? The inverse of this one will be the transfer function. Okay? Yeah. So for this particular case, it's not my lecture notes, it's coming out of the nowhere here. So let's see, if I want to find the inverse Laplace, okay, so h of t equal to the inverse Laplace of this one here, okay, this one here, okay. So the first step, I think what you need to do is, this is actually already a pretty simple format already, right? Yeah. What you're going to do next is, you're going to have to look at what kind of roots you have for this denominator, okay. So you set the denominator to 0, so this is 3s squared plus 4s plus 2 equal to 0. So what kind of S solution for this one here is? So negative b is 4 plus minus, well, negative 8, right? And then, sorry, negative b, yeah. So b squared minus 4ac, so 4 squared minus 4 by 3 by 2 divided by 2a. So divided by 2a, so 2 by 3. That's the formula. Okay. So what do we have? This is 16. This is 4 by 2, 8. So you have a complex conjugate roots here, right? Yeah, complex conjugate. So you're not going to decompose this into two brackets. Okay. So you can just stay. So you can just let it the same as it is. Okay, the same as it is. Okay. And then the next step. So the next step, what you do is you're going to have to make use of the table now. Okay. So what do? We first, okay, transform the denominator, okay, into what we want. Okay. So I think I'm going to take the s, the 3. Yeah, this is not very convenient, but if I take the 3 out, okay, so 1 over 3 at here, the bottom here becomes s squared plus 4 over 3 plus 2 over 3. Okay, is that right? Yeah. And then the bottom here is s plus 2 over 3 squared. Okay. So why? Because when I expand this term here, I got s squared plus 4 over 3s back. But and then I have to plus a 4 over 9. So that I have to minus a 4 over 9 plus 2 over 3. Okay? Was that okay? Yeah. So what's 4 over 9 plus 2 over 3? So 2 over 3, so multiply by 3, that's 6 over 9. So this is 2 over 9. This whole thing is 2 over 9 here, right? 2 over 9. Okay? So 2 over 9 here. Okay? And what we're going to look for the inverse Laplace transform. So I think what's coming into your mind, you should use which one? The sine omega t Laplace transform. So for this particular 2 over 9 here, this 2 over 9, which is what? Which is root 2 over 3 squared. Okay? Yeah. Okay, so this is root 2 over 3 squared, and I think I need a root 2 over 3 on the numerator, okay, in order to use the Laplace table. But if I put the root 2 over 3 here, then I have to, okay, cancel that out somewhere else. Okay. So then overall, what's inside the bracket? What's inside the brackets match what we want now. Okay, match what we want. Was that clear? Yeah. So this is basically the format for omega over s plus a squared plus omega squared. Okay. Yeah. So then the inverse Laplace. So this 3 by that's 1 over root 2. So these 3 cancel 1 over root 2. And altogether, what's inside here is e to the power of negative 2 over 3s sine root 2 over 3t. Okay. Anybody has a Laplace table? Just make sure I did it right. This thing's frozen. Was that right? Yeah, I think so. Yeah. Okay. So that's how you do. Okay. in general. Still frozen. Okay. Any questions? Okay. Yeah. So take a look at the lecture notes. I have another example. Okay, regarding a typical system. Basically, this example kind of combines things together. So you have a mass spring damper system, and asking what is the transfer function, what's the impulse response, like what we did here, and then overall giving a different input to the system, what will be the overall response of the system. Okay, so what I need you to be careful here is, okay, so that's right, Yeah, that's right. Okay, yeah. So what I need you to be careful is, one part of the question is basically, what's the impulse response? Okay, so that's basically, you know, a kind of thing question you should ask the impulse. And the other kind of a question is, what's the system response? Okay, yeah. Now these two are not the same thing, all right? Not the same thing. So if you have y double prime plus ay prime plus by equal to f of t, okay? So what's the impulse response? Then you look at the impulse, you look at the transfer function, right, to get the impulse response. But then if the question is what's the system response, then you're going to have to see exactly what's the input now to get the system response. So that clear? Yeah. So that's a difference here. Okay, that's a difference. Impulse response depends on the transfer function, and transfer function does not depend on the input. But system response, that depends on the system input. Okay, you have to know the input in order to know the system response. Okay. Okay, I'm gonna skip that example here. So that's basically impulse response and transfer function. Okay. Any questions? Okay, all good? Yeah. So usually the last few lectures are a little bit overwhelming, and because you know all the knowledge point basically we learned already. Okay, it's pretty much just applying those knowledge point to a slightly new concept here, right? Yeah. However, the next thing I'm going to talk about is sort of a brand new here, right? It's kind of blended into the lecture, okay, which is called Fourier series. Fourier series. Okay. Yeah. So you learn Taylor series, right? You learn Taylor series. So what does the Taylor series do to a given function? What did you do? When you apply Taylor series to a given function, that given function is transformed into a series of what do you call that? Powers, right? Yeah, powers. Basically, it's basically kind of power series, right? So that's Taylor series too. Now, same thing here. Now we have this Fourier series. Basically, the idea is, if I have a periodic function, so that's the difference. Okay, so the Fourier series is applied to a periodic function. Okay, so for a periodic function, then what we can do is we can transform it, okay, into a sum of harmonically oscillating functions. Okay, so it can be approximated by a sum of harmonically oscillating functions. So I said it's harmonically oscillating function, but in plain language, basically it's a sum of sines and cosine. Okay. So in other words, basically it's sines and cosines. Okay. So that's what the Fourier do. Okay. Yeah. So it's invented by the French mathematician Jean Fourier in 18 something. Okay. Yeah. So been a while. All right. Now, what does Fourier series do, or what kind of application can you use the Fourier series in engineering? There are actually many. The original application of Fourier series is being used to study the heat transfer or the temperature change on the plate. Okay. So before the Fourier series is invented, and how the temperature is distributed on the plate, right? And it's hard to solve, but once this one is done, and people can analytically derive something there. Actually, in 248, we had one of the equation called the Laplacian equation, right? Remember in the last lecture, the Laplacian equation, the second order one, the del square F. So that's basically an equation can be used to represent the heat transfer of temperature change on the plate. It's partial differential equation. Okay, yeah. So the Fourier series can be used to solve partial differential equation, which we won't be able to cover in this class anymore, right? And there are some other applications in electromagnetism and statistics, and so Fourier series here, right? The study of the Fourier series is a branch of mathematics called the Fourier analysis, essentially, right? Yeah, so it's a pretty wild a branch here. But we're going to just have a little peek of this Fourier series, but that's basically the spirit of Fourier series here, right? Yeah. First of all, we don't have much time, but first of all, we talk about periodic function. I think we need to understand what do we mean by periodic function. Okay, so if I have a periodic function g of t, and the period is, let's say, is t naught. Okay, then basically this g of t will equal to g of t plus t naught, right? Yeah, so that's periodic. That's what periodic function means. Okay, so at any time at this g of t function, okay, any time, it doesn't matter. If you shift yourself by a quantity of t naught, okay, then you end up with the same value, right? That's periodic function, right? Okay. Okay, so then the thing here is, so what do we mean by approximating this g of t with a sum of sines and a cosine here, right? So I'll give you what this means at here, and this is basically the Fourier series. This is the definition or the theory, doesn't matter what you call it. Okay, this g of t, okay, can be approximated using a sum of series sine and cosines. So it is equal to a naught plus infinite n equal to 1 and a n, okay, cosine n omega naught t plus b n sine n omega naught t. Okay, so omega naught here is the frequency. That's the frequency corresponding to the t naught. So what's omega naught? What's the relationship between omega naught and t naught again? 2 pi over t naught. Okay. Yeah. Okay. So now this is basically Fourier series. Okay. So the periodic function g of t can be approximated using this expression here. So sometimes this is represented using g infinite t. Okay, g infinite t. So basically, if this is infinite, it's a very, very, very good approximation. But if you need a rough approximation, then what do you do? Instead of using infinite here, you can use a capital N. Basically, I say, how many terms do I want to use to approximate this original g of t, right? So what you do is use a capital N here. Could be 3, could be 4. Okay, all you need is change that infinite to n. Okay, and nothing changed here. Okay, so that's Fourier series, right? Yeah. And the next question is, what is a naught? What is a n? What is b n? So if you look at this expression here, what do we know? We know omega n because the omega n comes on period of this periodic function. So all we don't know is what's a naught, a n, and b n. Once we figure this out, that's it. Okay. So I'll show you next lecture. Okay.